All right, so we're on section 1.3 today, and 1.3, I want you guys to know I'm sacrificing my lunch for you guys. You'll feel pretty special, right?
Yeah.
I'm happy to do that. That's my stuff at the house. So we're going to have at the very beginning of section 1.3 in the book, we have a postulate. And so you're going to find as we go through geometry that you're going to have postulates and theorems and definitions. And here's my recommendation. Write it down. Write it down and keep it close because did I tell you guys about being able to use an index card? Did I mention that last class? So you've got all these postulates and theorems and definitions and it's really hard to keep it all straight. And some teachers are cruel. It's cruel and unusual punishment. And they say, you're going to have to remember all of that when you take the test. And so there's no index card or cheat sheet or anything. Well, I am not that cruel teacher. Okay? Yes, a round of applause with you. No, please hold your applause, please. But so what I'm going to let you do is I'm going to let you have a little index card on your test. All right? And what I recommend putting on your index card is going to be primarily these definitions, the things that are boxed in the book, right? So if you look in your book and you see this little box here that says postulate, they do a pretty good job of boxing stuff off like that when it's important. Or bold definitions may be important as well if you don't understand it, right? So the point of the index card is not a lot of room, but it's enough room for things that it's like, I just can't remember this, or, this isn't the only class you're taking, I get that, right? So it's important things that haven't stuck with you. You want to put those on the index card so when you go to take the test, you'll have that there to reference and help you remember. It is just an index card on one side. If I was you, I wouldn't get the 3x5s, I'd get the 4x6 index cards. So you get a little bigger one, right? Fit a little more on there. If you're like me, man, when I was in college and they told me I could use a cheat sheet, it was amazing how tiny I could write, right? And get as much information on there as I wanted to. But I would recommend that you organize it well so that when you're taking a test, it's going to be easy for you to find the information that you're looking for, okay? But just remember that going forward. If you will take good notes up to that point, then it'll be easy to transfer it over to your index card. Yes?
So just one index card for all the box thingies?
That's right. Yeah, or whatever you want to put on there. I don't care. Whatever you want to put. You can put an example problem on there if you want to. I'm okay with that, right? If you're struggling with a particular problem, I'd like to be able to reference this.
Yes. One side of one index card.
One side of one index card. Yes. Yeah, just one side. All right. So like I said, I would recommend the 4x. I don't want anybody coming that someone found like an 8.5 by 11 index card. No, that's a piece of paper. We're talking about an index card, so about like that size, right? All right, so let's go on to talking about segments and their measurements. And so postulate 1 is the ruler's postulate. So again, those are all things that are going to be important. And as it turns out, for these things, the name can be important too. So you may think, well, I don't need to know that it's called the ruler postulate. I just need to know what that means, right? So you write down the fact that it says the distance between points A and B is written as AB or something like that. But the name can prove to be important when we're doing proofs. So one of the things that geometry has a lot of is proof, right? We will give you a set of conditions at the beginning of the problem, and then we'll say, prove that this is true based on these given items. And the way that you do that proof is you start kind of piecing together, it's like that logic stuff that we did last week. You start piecing together an argument for why the final statement is true. And the way that you piece that together is you say, well, this and this has to be true because of the ruler postulate. So those names are going to be important when we're doing the proofs, right? Ruler postulate is probably not one that you're going to use, but you'll see as we start hitting some of these theorems and all how it's going to be important to remember that name so it's easy to kind of explain the proofs. But what does the ruler postulate say? It says the points on a line can be matched one-to-one with the real numbers. The real number that corresponds to a point is the coordinate of the point. So this is just stuff that we should already be familiar with, but it's saying like if you have a line here with a point A and a point B, those are the coordinates on the line, and those match with, in the case of this horizontal line, we might represent those coordinates as as x1 and x2. So they've got a couple of bold words here, and coordinate is something that you need to be, at least know what that means. Most of you are probably familiar with that term already, right? The real number that corresponds to a point is the coordinate of the point. So the real number corresponding to point is the coordinate, all right? The other thing this postulate says is that the distance between, and I like to write, abbreviate between is b/n, between points. I would get good at abbreviations, by the way. If you're going to cram this onto an index card, abbreviations are going to be your friend, right? So, like I said, right now, points, PTS, points A and B, the distance between points A and B, written as AB, that's the way we represent that distance, is the absolute value, ABS value, hello, the ABS value of the difference between the coordinates of A and B. So that should sort of make sense to us. You know, if this was a number line here, and this point was 3, and this point was 5, then we would say the distance between point A and B is 2, right? The difference of 3 and 5. And it says the absolute value. If you did the absolute value, it wouldn't matter which number you subtracted from the other. If I do 3 minus 5 and get a negative 2, as long as I take the absolute value of that, get 2, the distance is still going to be 2. AB is also called, bless you, the length of AB. And what does AB with a line over it mean?
AB are points of the line and points.
AB over the line is a segment.
Segment, right. So that's what I was looking for, a line segment, right?
Right.
Right? That's what you were talking about, that distance there. But the term that we use, I just want to make sure that you guys remember that term, line segment, right? That was one of the problems on the quiz. And so this is more about terminology, just making sure that you understand what that terminology means. And so there's an example in the book here where you use a ruler. You know, I'm going to assume that you guys have used a ruler before, and that if you have a problem in the book, then here's your line segment. It says how many millimeters is this, that you're going to be able to stick your ruler down there and figure out how many millimeters that is, right? And so here in the book, the example is they're measuring this line segment, and it's about 2.5 centimeters. And so the way, just they're highlighting the fact that they measured it on the ruler between points 3 and 5.5, right? And so they found the distance of the line segment by saying the absolute value of 5.5 centimeters minus 3 centimeters is going to be 2.5 centimeters. And so just make sure you can do that. If you can't do that, you need me to elaborate more on that, we can do that after class, all right? But like I said, this is pretty straightforward as far as using the ruler. I should say when we use the word postulate, that's kind of a weird word and maybe one that you're not familiar with. You also may see the word axiom, and it's just a rule that we're gonna say this is the way it works, and we expect you just to accept that. We're not going to prove it. Other things we're going to say, here's the theorem and here's the proof for that theorem. This is why we say that this is true, right? But for postulates and axioms, they're just basically statements that we make that you can just accept as being true throughout the course. All right? Any questions about that? All right, so let's give you another postulate, which is postulate number 2, which is the segment addition postulate. Segment addition postulate. And a lot of these to start with, they're going to be sort of common sense, right? And all this says is that if I have I'll write out what they say here. B is between A and C, then AB plus BC equals AC. If AB plus BC equals AC, then B is between A and C. I'm going to write down a little graph of that, like we have here in the book. A, B, and then C. Let me see, this is AC, this is AB, this is BC. And so the way the postulate is worded, they make a statement at the beginning of it, and then they basically make the reverse of that statement at the end, right? So if B is a point between A and C, this is supposed to say then AB, the length, remember AB without a line or anything over it represents the length of the line segment. We said that right here. AB is also called the length of AB. See where the definitions are going to sort of be important? You're going to have to know that an AB without a line over it means the length of the line segment, whereas this means the line segment itself. One, we're talking about the number that represents the length. The other one, we're identifying that line segment. Okay? But the length of AB plus the length of BC will equal the length of the whole thing. So it just means you can add those pieces together to get the total length. That's all it's saying, right? Pretty, right? Really? So some of this is just kind of straightforward and obvious. But when we're doing proofs, you can't just say, well, that should be obvious, and I can skip over saying that that's the conclusion that I'm drawing. You have to say AB and BC added together equals AC because of the segment addition postulate. So those are the types of things that you have to list on proofs, okay? So it's important that you remember what the segment addition postulate is about. And so again, as I'm kind of writing these things on the board, I'm giving you the information that's in the box. But my recommendation to you is if you can say that in your own words in a simpler fashion, or know it in your mind just by drawing the picture, then do that because it'll save room on your index card, right? All right, so any questions about the segment addition postulate? Pretty simple. So they have an example in the book, finding distance on a map. But again, you guys are pretty bright. I'm not concerned about you understanding how to do that. It is kind of cool that this book, I don't think these authors are from Georgia, but the example they have in the book is actually the distance from Albany, Georgia to Athens, Georgia, with Macon in the middle. And so they identify that it's 90 miles from Albany to Macon. They draw a straight line on the map. It goes right through Macon, 90 miles from Albany to Macon, and then 80 miles from Macon to Athens. And so what's the total distance between Albany and Athens? Well, because of the segment addition postulate, we know that it's just going to be 90 plus 80, which is 170. So you can look at that example in the book. Questions? All right, now we got a formula. So again, the boxes are going to be really important, right? The distance formula. So this one's going to make sure that you know how to do this. Maybe you've already seen it before. Who's heard of the Pythagorean theorem? You guys familiar with that, right? You guys should have all seen that at some point in your mathematical experience. But remember, the Pythagorean theorem says if I've got a right triangle, and I label my sides A, B, and C, those are the length of each of those sides. Who can tell me what the Pythagorean theorem says? Yes?
A squared plus B squared equals C squared.
A squared plus B squared equals C squared. So tell me your name again, buddy?
Aiden.
Hey, you're Aiden. And you answered something for me a minute ago. What was your Cameron?
Yes, sir.
You're Cameron, and you are
Jody.
Jody. Right, Jody. So the length of the smaller side squared will equal the length of the hypotenuse, the longer side squared, right? And so the distance formula is based on that, and it should look similar. So if you've got a point, if A, which is just a point, x1, y1, and B, which is another point with coordinates x2, y2, are points in a coordinate plane, or points in a coordinate plane. The distance between the two is represented by this equation. AB equals the square root of x2 minus x1 squared plus y2 minus y1 squared. And again, we can do a drawing here because drawings sometimes can kind of help you understand it better. And the drawing really helps you see how this is based on the Pythagorean theorem. So we've got a point A, we've got a point B, so I'll let you guys kind of get caught up writing. So we've got those 2 points, and we're trying to find the distance between the two, right? The length of this line segment here. And so you can think about it like this. I'm going to kind of do this dotted, because that's really the line segment that we're interested in. But what is this length here? Well, this length here is the absolute value of the distance, the difference between the x coordinates, right? So x2 minus x1 is that distance. And this distance here is the difference between the y coordinates, so the absolute value of y2 minus y, I did y squared, I should have done y2. y1 minus y2. And so if you think about it like that, it should be sort of obvious to you that this is really just the Pythagorean theorem, right? Which says that this distance squared plus this distance squared equals this distance squared equals AB squared. But in order to find AB, you take the square root of AB, you get rid of that square, and so it's the square root of those values, all right? So if you're not connecting the dots with the Pythagorean theorem, yes?
With the, for the y, wouldn't it be y2 minus, okay.
Yeah. Yeah.
Just making
Whatever
sure.
order you do one, you should do the other. In this case, it didn't matter because we're taking the absolute value of it because we're just showing you the real distance there.
Right.
But yeah, you should always, whenever you're subtracting those, you should always use the same point. So good catch. But like I said, whether you get the Pythagorean theorem or not, if you're good with the Pythagorean theorem, yes.
So it says a
I can tell by
squared.
the way it said so. This is going to be a long one. So what you got, David? I'm gonna take a rest here.
A squared plus b squared equals c squared.
Mm-hmm.
So what you do to one side of the equation, you have to do the other, right?
Right.
So why can't you just take away the squares?
Well, because you're taking the way square roots work, a squared plus b squared equals c squared. Well, I'm gonna put my c squared here so that it'll match our distance point. C squared equals a squared plus b squared. When I take the square root to get rid of that square there, I have to take the square root of the whole thing. All right, and so it's c squared equals the square root of a squared plus b squared. What I can't do, there's no rule in mathematics that says I'm able to change this to the square root of a squared plus the square root of b squared, which is what you're trying to do. Right, it's because there's addition right here, we can't just remove the squares because we took the square root of it. Now if they had been like this, if it had been c squared equals a squared times b squared, and then we've taken the square root of both sides, then yes, we could have just said that equals c equals a times b.
Got it.
But you can't do it when it's addition. Okay?
Okay.
All right, good question. So like I said, whether you are good with the Pythagorean theorem and just get this and can remember this formula based on the Pythagorean theorem or not, doesn't matter. Just make sure you understand the formula, right? If you've got 2 lines, if you've got 2 points, you can find the distance between those 2 points using this formula here. So let's actually do an example so we can put it into practice and make sure we get it. And the example is number 3 on page 19. And that says, find the length of the segments, tell whether any of the segments have the same length. So for time's sake, we're not going to find the length of all the segments. We're going to just do one, and we'll do the short guy, because you know the short ones always get overlooked. Everybody's trying to do the bigger one, but we're going to be kind to the little guy and do him. So we're going to do AC. All right, let's find the length of AC. So the length of AC, based on our formula there, is going to be the square root of, I'm going to go ahead and just write in all the pieces here, the difference of the x's squared plus the difference of the y's squared. And so it doesn't matter which point we start with, we just have to make sure we start with the same point but you know what, let's just write this down. x2 minus x1, y2 minus y1. All right, that way we can just plug in our values. So x2 is, you guys see the one we're doing, so we're doing this one here, which is -1, 1, and 3, 2. Right, that's the one that we're going to do. All right, so x2 is 3 minus x1, which is -1. So we're going to put that in parentheses there so we don't forget about the negative sign, plus y2, which is 2, minus y1, which is 1. We're going to square that. And so, again, take all the steps so that you don't make a dumb mistake with your negative signs. 3 minus a -1 is the same as 3 plus 1. So this is going to be 4 squared plus, and 2 minus 1 is going to be 1 squared. So that equals the square root of 16 plus 1. So the square root of 17 is that distance. All right, since 17, you can't pull out any number, we can just leave the answer like that. If this number was, if it was the square root of 16, obviously I want you to write it as 4. Or if it was something like the square root of 20, if it's the square root of 20, I would want you to recognize that that's the same as the square root of 5 times 4. And since we could take the square root of 4, I could rewrite that as 2 square root of 5. Okay? So always simplify the radical if you can. You can pull anything out from under it. Go ahead and do that. Get in the habit of doing that. Any questions about that problem? Yes.
So if you put, whether you put A, B, B, C, or anything, it'll still be x2 minus x1 squared plus y2 minus y1 squared?
Mm-hmm. Yep.
Okay.
Yep. And like I said, you can make either point. I could have made this point. I chose to make this point x2, y2, but I could have said this was x1, y1, and I could have said this was x2, y2, which would have reversed the order in which I did the subtraction here. But the number, since we're squaring it, the number is going to end up being the same, right? As long as you start with the same coordinate. Okay, so let's see. The distance formula of the Pythagorean theorem, they just go through the next section there, exactly what I've already done with the Pythagorean theorem, just showing you that these are the same thing, right? I could rewrite this. I could draw my little triangle as CAB, and it would be a squared plus b squared equals c squared, and so c equals the square root of a squared plus b squared, which is in essence what this is. So that's all that little next box is showing you what we've already gone through there. Let's do, so that's all really from chapter 1.3, sorry. Let's go to move to 1.4. So angles, I did not tell you guys to to bring your, what is that thing called? It's got little angles on it.
Compass.
Protractor.
Which one is it?
Protractor.
It's the protractor, but I always want to call it the compass because it makes me think of a compass and how the little needle moves around, and you got your little measurement that you're doing. I always want to call it a compass, but it's not. It's a protractor. What's a compass? You guys got a compass with you? Yeah. So it's how you can draw circles, right? You can adjust the angle and draw things like that. So this one, if you don't have your protractor with you, that's okay. But you will probably need one to do some of the homework classes, right? So we're going to talk about angles and using your protractor. And this is, like I said, section 1.4. So we're going to start with some terminology. An angle got point A right here, we've got a point C, a point B. So this point here, it's called the vertex. These are the sides. Form an angle, the rays basically that the angle is made up of, we call those the sides. And of course this distance here, this is our angle, right? And so there's multiple ways that you can represent this angle if you want to write it down. If I asked you to give me the name of that angle there, you could tell me that you would write this little angle symbol, right? And you could tell me that it was angle CAB. You could tell me that it was angle BAC. Notice with both of those, the vertex always goes in the middle, right? So if you're going to list it like that with 3 points, make sure your vertex is always in the middle. You couldn't say ABC because that would suggest that B was the vertex. So CAB or angle BAC would be acceptable. Or since we've got this point labeled where the vertex is, you could also just say angle A. All right, so any of those would be acceptable ways to define that angle. And so they have a problem in the book where they label it like this, and they say P, S, R, and then this point's Q. And they said there are 3 different angles. And so our 3 angles are, obviously this top one here, this bottom one here, or the whole outer big one, right? So those are our 3 angles. Now, here's the main point with this one. Can I say angle Q? No. For any of those? I can't because I don't know which one it applies to, right? So we got 3 angles that are sharing that vertex. So if I told you to list those 3 angles, you'd have to say like angle PQS, which would be this angle here, right? This one here. And then you could say the next one is, if I want to do this one, SQR. And then last of all, we do this big outer one here, which is going to be angle PQR. Or I could say RQP. Doesn't matter as long as the vertex is in the middle. Okay, so just make sure you know how to write those down. Now, if we use our protractor and we measure our angle, angles are measured in what? What units? Usually. What? Degrees, right? So tell me your name again? Joshua. How can I not remember your name is Joshua, Dan? Since I've got a Joshua. It's just wrong. So we measure them in degrees. We can also measure angles. Does anybody know what else you might measure an angle in?
Inches.
Huh? Yeah. Yes.
Is it radians?
Radians, yeah. So if you get a scientific calculator, you can change it to either use degrees or use radians. And so in here I think we're pretty much going to stick with degrees the whole time. But in some of the other math classes, you may have to switch to radians. But anyway, does everybody understand how to use your protractor to check an angle? Does anybody need me to go over that? I don't mind going over it. You want me to go over it? No?
No.
If you want me to go over it, raise your hand. Who wants me to go over it but they're scared to raise their hand? Who won't raise their hand to say they want me to go over it because they're scared to raise their hand by raising their hand? Did I say that right? No. All right, I'm going to assume that you know how to do it, right? But there is an example in the book. But if we've got two angles that have the same measurement, so let's say, for example, this one here, if I made this a little bit bigger, that looks pretty good. If these angles had the same measurement, then I can say that those angles are congruent. That's the term that I would use for that. So congruent angles And again, abbreviations, so I'm just going to abbreviate it like that. Congruent angles have the same measure. Now, so make sure you understand what congruent angles are. So that means, like, if I measured this one here and I said this was 40 degrees, if I told you that they're congruent, then this one here is also 40 degrees. Okay? And I wouldn't have to write the degrees on there to show they're congruent, though. Actually, all I have to write is that little line. Now, if I had done one line for one and two lines for the other, that would tell you that they're not the same angle. Okay? But if you see a problem and I've written just a single line for each one, it's kind of a curved line, right? I guess that's technically not a line. If I write a single curve for each one, then that means they have the same measurement. And so in this case here, now that I've drawn it like this, I can say that angle PQS is congruent, and the way that I draw that is an equal sign with that little tilde symbol over it. The tilde is on it's on your keyboard on the top. If you hit your shift key and hit usually the number 1, it has the little tilde on top of it. But angle PQS, this angle here, is congruent with this bottom angle, which is SQR. So that's how I would write that. That's how I would say those two angles are congruent. But if two angles are congruent, that means their measures are equal, right? So if this is true, if angle PQS is congruent with angle SQR, then that means that the measure of angle PQS is equal to the measure of angle SQR. So when we're talking about the actual measurement, we're talking about the number of degrees that corresponds to that angle, we write a little M in front of it, saying we're referring to that physical length, that physical distance, okay? And when we're talking about measurements, we don't talk about congruency. When we talk about measurements, we say they're equal. All right, so the angles are congruent, which means they have the same measure, and the measurements are the measures are equal. All right, this may be kind of a weird distinction, and maybe you think it doesn't matter, but I'm just saying you're going to see this type of stuff all the time throughout the course, right? And I'm going to expect you to know when to write the measure, right? One of the things that are we learning that postulate now? Let's see. No, that's not in here. But there's going to be a congruency postulate. And the congruency postulate, or theorem, maybe it's a theorem, I can't remember. But it's going to say that if you know that two angles are congruent, then you can say their measures are the same. And that's something that you'll use in your proof. Okay? So make sure you understand the definition of congruency. Congruent angles in this case. Any questions about that? Thank you guys for trying to look interested, right? Yeah. I know it can be hard with some of it. All right, so the protractor postulate, which is at the top of page 27, that looks pretty similar to the ruler postulate that we had earlier, right? And it's in essence making the same statement, but about angles instead of measurement of length on a line segment, right? So the protractor postulate just says that It just tells you basically how to read your protractor, right? So I'm going to let you, I could rewrite everything that's in the book, but the thing that you need to make sure that you understand is that if you have this angle here, right, which they've labeled O, B, and then there's a point A right here. The measure of angle OAB, so the measure of angle, not OAB, AOB, measure of angle AOB is equal to the absolute value of the difference between the real numbers for OA and OB, ray OA and ray OB. So ray OA minus ray OB. And really for that to make sense, I need to draw the protractor behind there, which is going to be challenging. All right. So let's see. Wow. This is a lot of pressure, you guys, right here while I'm doing this, you know. So we're going to do this kind of around this way, like that. Like that. And then we got this here. And do that around that way. And so we've got our little tick marks on here, right? So the point is these rays, they have it on your compass, on your protractor, these rays actually have a measurement on there. So like this one, for example, OB, in the way we've drawn this one, we might say that this one's 0 degrees. And then based on where this is over here, you know, they've got it drawn at like 112 degrees, right? And so all this postulate is saying is that I can get the measure of this angle here by taking whatever the value is at ray OA, which in this case is 112, right? And subtracting from that the value of ray OB on my protractor, which is 0 degrees. And so that the measure then of angle AOB is 112 degrees. All right. And so if I were to let's say I rotated my protractor, right, and now this was instead at 10 degrees, right? If I rotated it and this was at 10 degrees now, then for this angle here, this guy is going to point over here to 122 degrees, right? But I'll still get the same measurement when I punch those in, because it'll be 122 minus 10, and it still gives me 112. So it's just saying you can use your protractor like that and figure out the measure of an angle. Does that make sense to everybody? That's a tough one to write on the board, but it's a simple concept. It's just saying you can read your protractor and figure out the measurement of the angle, right? All right, so another definition here is that if I have an angle, like this one here, and I have a point out here, say point D, and I have a point here, point E. E is, how do they write that? E is a point in the interior of the angle. And D is in, what do they say, in the exterior of the angle. The one point's interior to the angle, the other is exterior to the angle. Makes sense, right? Anything in this area here is interior. Anything out here is exterior. Pretty straightforward, but just definitions. I gotta make sure you understand, so that we can give you another postulate, right? So postulate number 4 is the angle addition postulate. Angle addition postulate. You see now why I'm just super nice by letting you guys have an index card? This is a lot of stuff to remember, right?
Just in the first 2 lessons.
Right, we're only in the first 2 lessons. So imagine by the time we get to the end and we're ready to take a test, or even worse, you will be able to have a bigger sheet for your like semester exam. So you'll definitely need more room for that. But here's my take on it. You're going to memorize this stuff just for the test, and then what are you going to do? You're going to dump all of it if I make you memorize it, right? So at least if I get you to write an index card, you can save those for the future if you ever need to do geometry again. Yes?
So for each individual quiz, can we make a new one for each quiz, or do we have to?
So for, well, I will tell you on the quiz. The quizzes may work a little differently. I may kind of give you the information versus you having to use your index card for the quiz.
Okay.
So we'll see. We'll kind of play that by ear. I'm not sure how I'm going to do it on the quizzes yet. Definitely on the test, you'll get an index card. I'm not sure about the quizzes.
Okay.
But yeah, if I allow it on what would probably make the most sense on an index, what would probably make the most sense would be on your quiz, try to do a portion of your index card. And then you don't have to redo an index card every time. And so maybe you could sort of like slowly build your index card right as you're taking your quizzes so that you've already got it put together by the time the test gets here. But we'll see. All right, so let's do the angle addition postulate. And that says, if I have something, a couple of angles that look like this, and I kind of drew that wrong. Well, I drew it wrong, but it's based on stuff that they've got in here that's not really accurate with what I've told you. That's fine. Let's see. I'm talking to myself, just ignore me. I'll figure out in a minute what I want to say. PRPTS. Measure of angle RSP right here. And then right here, we have the measure of angle PST. And so if P is in the interior of angle RST, then the measure of angle RSP plus the measure of angle PST equals the measure of angle RST. So the whole point of that postulate, right, is that I can take those two interior angles and add them together, the measurement of those, and I will get the measurement of the entire outer angle, right? That's the point. These two measurements added together will give you the measurement of the whole thing, angle RST. Questions about that? Again, this is kind of common sense stuff that we already know how to do. But they do give us an example here that we can test it and make sure we understand what it's saying. So let's do that. It's example 2 on page 27. And it says, don't I have some horse people in here? Aren't the people that said they did a horse camp or something, right? So we've got an example with a horse, right? So you guys should be totally into this. I'm not going to draw the horse head like they did. But they say each eye of a horse wearing blinkers. I thought they were called blinders, so they're called blinkers?
They're called blinders.
It's their
My brother would call them shadow rollers.
shadow what?
Shadow rollers.
Oh,
I think
interesting.
it could be called a bunch of different.
Yeah, I have never
It's
heard
like
blinkers
blinders.
before. Has anybody heard that? Blinkers for a horse? All right, so blinkers has an angle vision that measures 100 degrees. The angle vision that is seen by both eyes, so each eye has an angle of vision that measures 100 degrees. So we got the horse up here, right? Here he is. Here's his ears. We'll give him really big ears. He's kind of coming around here. There he is. He's kind of, what are you laughing about? Give him some nose holes so he can breathe. And the eyes are kind of hard. They're over here with these flat. Poor guy. We'll make his ears a little bit shorter because he's embarrassed about his ears being so long. All right. So So there we go. So now we're coming down here. We're looking this way. And we've got this region here. But then we've got, so this goes like to the middle of his head. And like that, and like that. All right. So the angle of vision that is seen by both eyes measures 60 degrees. And they ask us, find the angle of vision seen by the left eye alone. So each eye of a horse wearing blinkers has an angle of vision that measures 100 degrees. Find the angle of vision seen by the left eye alone. So this is a weird, the way this is phrased is really kind of, the total vision for the left eye is 100 degrees, right? But then but their question, see the way that this is what they're saying. They're saying that this distance here, this distance is 100 degrees, right? And this distance is 100 degrees. But then this distance in the middle here is what? 60 degrees. But then does anybody else think this is a strange problem? Because they say at the beginning, each eye has an angle of vision that measures 100 degrees.
So like,
What they're trying to get you to say is they're trying to say if I just look at the left eye, if I try to find this measurement here, then that measurement's obviously going to be what? If this total is 100 degrees, and this takes up 60, so your total would be, so this area over here would be 100 degrees minus 60 degrees equals 40 degrees. And that's the answer.
Okay.
But it doesn't make any sense because they tell you at the very beginning, each eye has an angle of vision measuring 100 degrees. So find the angle of vision seen by the left eye alone. You just told me each eye is 100 degrees, so wouldn't the left eye alone be 100 degrees? I'm very confused at how they lay out this problem. That's what they're trying to get you to say. Did somebody, you figured it out?
Yeah.
Okay.
So the eyes overlap.
Right.
So they're both seeing that 60 degrees.
Right.
Both of them can see that.
Right.
And you're trying to figure out what only the left eye can see. Because the right eye can technically see in that 60 degrees.
Yeah.
So they're trying to figure out, find the 40 degrees that only the left eye can see.
Okay, I see what you're saying. So they're not saying that the left eye can only see 40. They're not saying that if he closed his eye, he would only see 40 degrees. He would see 100, but they're just trying to say what's just the portion that only the left eye can see and the right eye could never see. Okay, good.
Yes.
That makes more sense. I just think that they asked the question in a way that's not as obvious. So tell me your name again.
Jackson.
Jackson. All right. Everybody follow that? So Jackson's going to teach the rest of the course because I couldn't figure it out. And thank you, Jackson, because I wanted to eat my food anyway, right? So, all right, so let's see how much time. We've got 20 minutes. So let's go through classifying angles, and I think we'll basically be done. And you probably already know these classifications, right? So we may get done early. What happens if I get done early? I can't just let you little monsters out and wander
You get to
around
eat.
free. Huh?
You get to eat.
I get to eat, I know, but do you guys have to stay in here until the next
Sure.
class? Is that the way it goes? Okay. Yeah?
Chill out in
You
here.
could start on your homework,
Ooh.
Yeah.
Yay.
right? I can go and get your homework, you can start on your homework. All right, so let's talk about the different types of angles, which like I said, I think this is gonna be straightforward. You've already seen it before. There's only maybe one that you're like, oh, I didn't remember that. But, all right, so we're going to give each of these angles a vertex of A, right? And this one here, this is an angle. So for this one, the measure of angle A is in between 0 and 90 degrees. So what kind of angle is that? Cute. It's so cute. It's a cute one. All right. And then this one here, the measure of angle A equals 90 degrees, so that we know is a right angle. We'll put angle after each of these so we remember that it's a right angle. This is 90 degrees. Measurement is in between 90 degrees and 180 degrees. So that's called an obtuse one. So if someone tells you you're looking kind of obtuse, that's not a compliment, all right? And then finally, if the measure of the angle is exactly 180 degrees, this is the one that I didn't remember, then that one is straight angle. Which makes sense because it just forms a straight line, right? All right, questions about the labeling of those angles? So I'm not going to write it. I'm not going to write it down. We'll just look at it in the book. So, does anybody not have the book today? You don't have your book today.
We're gonna get it this week.
Oh, okay, gotcha. Is anybody else missing a book? You're missing one too. Can you just put yours? Which side is it on? It's on the left side. So actually, you should look over him. Sorry. So look to the person on your right. And glance at the problem there, so I don't have to write that big graph out of the board, right? So if we look at angle LMN forms what kind of angle?
The right angle.
It's a right angle, right? So, you know, I'll just draw, I'm not going to draw the actual. Draw like this, and then like this, and so we'll say MNQP, and then L. All right, there we go. So that'll be good enough, I think, without the lines on there. So angle LMN. Somebody correctly said that is. They don't write that down for us. So normally in most cases in here, they're not going to let you just assume that's a 90-degree angle without figuring out, without proving it, using the Pythagorean theorem, or they put a little box on there to identify it. But I guess it's early in the year, so they're allowing you to just eyeball that. But yes, that would be a right angle. Angle LMP. LMP, what kind of angle is that?
Right angle.
It's a straight one, right? Angle NMQ, and then L. MQ. So NMQ.
You're cute.
Yeah, he's so cute. That was easy to remember, right? A cute one, and then LMQ is the
Obtuse.
It's the heavy set one, right? So obtuse, a little bit more space in there. But he's still small compared to the straight angle, so it's always a bigger fish. All right, two angles that share a common vertex. This is one other thing I need to make sure I forgot about this. So if we have this, and we were to label that A, B, C, D. We would say that angle BAC is adjacent to angle CAD because they share a common side. These are adjacent angles. They share a common vertex and a common side because share a common vertex and side. Make sense? Yes.
Adjacent means next to or beside, right?
That's right. Yep, exactly. So yeah, if you can remember that definition, then you can remember what that means. Already got your name up here, buddy? What's your name?
Cal.
Cal, okay. All right. Any questions overall? All right, so your homework problems this week are, let's see. I'm like, where's my phone? Oh yeah, it's right here. So your homework's going to be from sections 1.3 and 1.4. And scroll, sort of. Oh, we got a ton of rock. Yeah. Nope. All right, so 19 through 41 on 55 and 6, and then 17, 18, 18, 21, 23 through 31, 23 through 31, all of those, all. 41, 43, I'll move out of the way in just a second. 41, 43, 61, 64, 67, and then 70, 72, 74. 70, 72, 74. All right? So you may go ahead and begin those. And you can go ahead and let me know if you have any questions.